This topic we will talking about the power and efficiency. Power is defined as the amount of work performed per unit of time, or it is defined can be calculated by uh, the derivative of work with respect to time. And since the works can be placed as the dot product for of the force vector and the position vector, du equal to F dot dr. So then the power can be written as du by dt. That is the dot product of F uh, of the force F and the first derivative of position vector with respect to time. That is the first derivative of position vector is defined as velocity. Okay, so then it means that the power is equal to the dot product of the force vector and the velocity vector. According to the dot product, we know that the dot product gives us the scalar quantity. Okay, so then the power is a scalar uh, defined as the product of force and velocity components acting in the same direction. So for the unit of the power, because it is defined as the 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 work per unit of time. So then the unit of power is defined in SI system as joule per second or watt. Okay, and in US customary system or FPS system, the power is usually expressed in term of horsepower. That is, 1 horsepower is equal to 550 foot-pounds per second, or 746 watts. The mechanical efficiencies of a machine is the ratio of the useful power produced to the power supply to the machine. Or in we can write as the equation like this: the efficiencies are we represent by the epsilon equal to power output, that is the useful power produced, okay, divided by the supply power, that is supply from the supply to the machine, okay, that is the input power. So from this equation, it is mean that actually the efficiencies of the mechanical system normally is not greater than one. It's normally it should be less than one. Okay, so let's take a look this example. A 50 kilogram block is hoisted by the pulley system and a motor. The motor has an efficiency of 0.8. At this instant, point P on the table has a velocity of 12 meters per second, and it is increasing at rate of 6 meters per second squared. So then increasing in velocity. So then it means that this value is the acceleration of point P. Okay, we will not consider the mass of the pulley and the cable. We would like to find the power supply to the motor at this instant. According to this problem, we starting with set up the reference line. Okay, we know that this point is fixed. So then we set up this is as the reference, and we know the velocity of point P. So we find the relationship of the length of the cable. This defined as SP. Okay, and this length defined as SP. Now we have SP. Okay, and we also have from this reference we also have SA, that is this cable. So according to these two lengths, we can formulate the constraint equation that SP plus 2SA equal to a constant length. Okay, so according to this, we can find the relationship of the velocity and the acceleration of point A and point P. Okay, by first derivative, we get VP plus 2VA equal to 0, right? Okay, and then it means that VA equal to minus VP over 2. Okay, so it means that from this we set up this line as a reference, and from the picture we measure from the reference to the point that we consider downward. So then downward as the positive direction. Okay, what does this mean? It means that when we set up, when A is moving down, okay, point P should move up because the negative sign means like that. Okay, so if A moving down, P will moving up, and if A moving up, P will moving down. Okay, so according to this, we found out from the problem give us that the point P is moving down, with 12 meter per second. Okay, so A is moving up with minus 12 over 2. So then A is moving up with 6 meter per second. Okay, and also for the acceleration, okay, for the acceleration, this is the same. Acceleration, we have acceleration of point A equal to minus AP divided by 2. But AP equal to 6 meter per second square. So then acceleration of point A is equal to negative 3 meter per second square. The negative signs mean that it's moving up. Okay. And after we consider the free body diagram, okay, we can derive the equation of motion that's for block A from the free body diagram. We found that equation of motion of block A become, we set up upward as a positive. Okay, so then equation of motion become 2t minus weight, that is 490.5 equal to 50, and time acceleration of block A, that is equal to 3, because now we know already that acceleration of block A is 3 meter per second square upward. So after we solve this equation, we get the tension. We get the tension in cable. Okay, and after that, we use the tension in cable to find the power supplied by the motor. Okay, the power supplied by the motor to produce force applied to the cable with the velocity of the cable at point P, that we now know from the problem that is equal to 12. So then it means that the power supplied by the motor to the cable, this is equal to the required tension, that is 320.3 Newton times 12, that is the velocity of the cable at point P. So then we require the power of 3,844 watts. Okay, this is the power that we require from the motor. But because we know that the motor has the efficiency of 0.8, so then the input power to the motor, the supply power to the motor should be greater than 3,844. So then what is this? From the equation that we know that the efficiencies is the power output divided by power input. So then we can solve for the input power that is equal to 4,804 watt. Okay, all simplified to 4.8 kilowatt. Let's complete this problem.